Mons is my university is located in in Canada, like province of Hainaut, where we are the capital of the Hainaut, and we are in the south of Belgium. So we do speak French, and as some of you know, that in the north we do speak Flemish or Netherlands, and we have a small part speaking German, 1% of the total population. So very complex country like Canada.
So, oui. Je m'excuse. Sinon, je peux l'arrêter.
Les gens voient?
Oui.
En fait, quand tu as enregistré, ça va planter.
Ah. Ça sera pas long.
Sur le José Haute, c'est le 12 mars, puis les full capacité salle, c'est 14 mars.
Sorry for this technical issue. So Mons is the capital of province of Hainaut, and we are very near France, Lille, as one of the major cities in France. Regarding the laboratory, we work like maybe some, more or less that we have here in Laval, at the university. So we have a center that are affiliated to different research topic, going from the down, fine organic synthesis, particularly a very big expertise in mass spectroscopy, going to plasma process. So we have some joint activity with the people working on plasma, so atmospheric plasma or even microwave plasma, up to my laboratory working on polymeric and composite matters. Regarding the staff, we are more or less 10 or 15 permanent, belonging as a professor, as also as FNRS, so like in France, the CNRS. And we have a total of 170 people. And in my laboratory, we are more or less 1/3 of the total of this center. And regarding the way that we carry out our research, mainly it's based on European project, regional project, because we are a federal country, but it's quite different than Canada. We have more money from the regional than the federal state. So that's the reason we have less federal contract. But to get an idea, we have published more or less 160 paper last year, and 1/4 related with my activity in polymer and composite matters. Regarding the department itself and the laboratory, so it's a laboratory that I co-head with Philippe Dubois, that is actually, in fact, the president of our university. And the aim of my laboratory is to design environmentally friendly and bio-source polymeric matters. This involves, of course, the chemistry in terms of sustainable chemistry in order to implement in nanotechnology and material science. Of course, the way that we are working is to cover the added value chains, meaning that we do a lot of fundamental research through Mons, from the University of Mons, but we do also a lot of applied research with Matanova. It's like, if you know the European country, the European system, it's like a Fraunhofer that are helping transferring our knowledge to companies. So in the case of my laboratory, we have 2 locations. So the University of Mons with this building, and we have another building very near, around maybe 1 kilometer by flight, that we are connecting, and we have small equipment available in this lab, in this building, and bigger equipment available in this building. Regarding the competence, we cover, as I mentioned, the synthesis, to the formulation, to the characterization. And of course, by covering the all added value shells, going from lab scale, so we can make, for instance, 5 grams of matters up to 300 kg per hour using this big extruder. And of course, we have also a platform that help us to understand the properties that we obtain at the final stage. And you can see the all value share. So as I mentioned, we can work with 7 grams of matters up to a couple of 100 kg of matters here. We can do also some specific extrusion like a T-extruder in order to combine different processes that are not compatible with each other and to try to combine. And you have also some post-processing unit like this mini injection unit and also related equipment like simulation, near-infrared, rheometer, and so on. About the catalyzation platform, we have the full catalyzation platform related with polymer, going from fire properties, gas permeation, and thermomechanical behavior. And also, thanks to the fact that we belongs to the CMAP, access to other type of equipment available in other laboratory, like AFM, XPS, and Malitot. Regarding the activity itself of the laboratory, we are covering more or less 4 topics, going from the micromolecular engineering, so design more or less new catalysts, organic catalysts instead of using metallic catalysts, for instance, in the case of biomedical application. We have also a lot of activity about biomedical application, like hydrogel, and also 2 other topics where we are very focused on polymer blend, nanocomposite, and implementation of such blend using reactive extrusion. As I mentioned, you can see that we have different affiliation, Mons, Matanova, and we have also a SME that is also linked to the university in order to commercialize some product that we have developed in the laboratory. To get an overview about the research, I will just mention 2 main examples based on the synthesis of bio-based using sustainable approach and the design of biopolymer with adaptable properties. So these are the examples that we have shown. So this is the first example that we have shown to carry out an enzymatic polymerization. So enzyme is like a catalyst, but very sensitive to temperature. And when you try to apply in a batch, in organic solvent, or if you use a very long polymerization time at high temperature, like the temperature that you can have in the case of extrusion, you can have the loss of the activity. And this is an example. By using reactive extrusion, we were able to get this polyester within 50 minutes. And just a very simple comparison, if you do the same in batch, it takes at least 2 days to get the final product. So that's a very beneficial effect. Simple polymerization, just we apply a process to improve, not only to improve, to boost the polymerization at the end. Of course, cellulose is very important in Canada. So we have a lot of activity related to the modification of nanofibers, particularly cellulose nanocrystals. But what we try is to have the best affinity and also the highest reinforcing effect that you can get in the case of nanofibers. So it means, je peux enlever un petit peu le masque parce que c'est.
Moi, je pense que tu peux. Peut-être juste vers les candelles, venir ici ou je sais pas.
So the means that the surface modification, we adapt the surface modification in such way that we have a real improvement. And this is an example where we modify in situ the cellulose and the crystals with lactic acid in a one-shot system. So we start directly from fibers and we do the modification in order to recover the S-modified nanocrystals. And by simply dispersing them in an extrusion technique, we can have an improvement. And in this case, the HDT, the heat diffusion temperature, that we strongly improve by adding a certain percentage of the nanocrystals. And what does it mean is that you can use PLA for engineering application, such as automotive parts, for instance. In the case of the second topic that we have also conducted, we have also a big expertise on adaptable properties based, for instance, on ultra-stretchable ionic system. So we can confer using this type of ionic interaction, new properties, new dynamicity inside the system, and then you can have a very highly stretchable matters that you cannot get with regular system based on the covalent bond. And this is the last example that we, for instance, develop some self-healing polymers, like when you scratch your skin, you have a healing process that can be carried out. In this case, using water, we were able to recover the system based on the peroxide system that can be used as a coating, for instance, to protect steel and so on. The example that I wanted to show is related to the topic that I was mentioning about metal-free catalyst and reactive extrusion, but today I will focus my talk on more specific on 3D printing and particularly stereolithography. Just to get an overview, we are able to design the matters and to implement into different types of 3D printing. And you have different technology based on fuse deposition modeling. So the generation of filament that you deposit each layer per layer to construct your 3D object. And you can see that you have the simple system that everyone can use at home, or we have the more complex inside the oven that can improve the printing definition and also the printing speed using this technique. We have also the selective laser sintering. That's some example technique that are used for metallurgy to join or to make sure bonding with metal granule. All is doing fine. Okay, that can be used like SLS. We have also bioprinter. And today I will focus on stereolithography that is based more or less on photopolymerization. The technique is very simple. You start from a batch that are containing photopolymerizable moieties like acrylic, monomer, for instance, and you apply a light. This is more or less a UV light that can initiate the photopolymerization. And depending on the position, you can create a certain object. And you create layer per layer. So you have the head where you have the first layer, and you move up your head in order to generate at the final stage this 3D object based on the illumination of matte that you use to create such object. Of course, when you create such object, you need to design and you need to create an STL file that more or less create a slicing of your object in order to get the final object like this sphere as examples. What is very important that as we develop our own resin or own matters, we need to work with open system, meaning that we can select the matters that we want and also the printing condition because it's depending on the resin in terms of composition and so on. This is the key. Of course, you have several advantages using stereolithography, simply the fact that you have a very high quality surface resolution, a very high dimension accuracy, and you can not lose the printing speed, as shown in these examples, where you make one Eiffel Tower or several tower, you can use the same printing time using this type of technique. So you can make multi-object in a one shot using stereolithography. And today I will focus more on my work involving chemistry and some adaptable properties that I will focus on 4 examples based on hydrogel actuators, based on conductive 3D print ionic composite hydrogel, a new concept that we are implementing in collaboration also with UBC ion-tronic touch sensor, and the final example that we are developing is structurally colored matters. So the first examples that I want to show is the actuators that you can obtain by 3D printing. So the idea to make such system is based on robotics. So you have different examples. The robots that you can develop by cornerstone that are able to have certain motion that will be to move in a certain area, like slow in Canada, for instance. Or you can have also some soft robot that is more or less based on a gel or something that is quite flexible, where you have a certain anisotropy, and you can have different type of structure that can be like these soft matters able to grab the X and leave the X and release the X in a soft way. Of course, when you look this type of matters, you need to create some complex structure having a certain anisotropy from soft matters. And this is an example This is the type of development that you can implement, as we call the first generation, involving more or less structural engineering, like this pneumatic system. This is in French, but I think that would be okay, where you need to combine a passive layer with an active layer. In this case, we inject, in fact, air that can inflate the layer and that can induce the deformation to get this movement from this sample. The video, I won't try to avoid use too much the video, otherwise I will be in trouble. This is another example. Or you can also develop, as we call, as a second generation, stimuli responsive polymer. More or less, you have an hydrogel that are sustain a certain stimuli, like a difference of temperature, difference of pH, that can change the shape. And again, you have in mind, to keep in mind that you need a certain active layer combined with a passive layer. That could be a bilayer, like these examples, or you can have some spars that are passive and active to get this final object that can have this type of shape after actuation. And today I will focus by combining the two generations involving structural engineering aspect and material engineering to create this 3D printing hydrogen. So this is the train station that we are expecting to get in Mons for a while, but we should have maybe 2 years soon a new train station, but in Belgium it's quite slow. Okay, to demonstrate the possibility to get this actuator, we took the polynipalm. So polynipalm is a polymer having, as we call, a LCST, a low critical solubility temperature. What does it mean? Is that when you pass a certain temperature, more or less above the body temperature, you have the insolubilization of your system. Of course, as an hydrogel, you need to add a crosslinker to sustain the deformation in the presence of water. And you need to use the right photo injector that are applicable using 3D printing related to the wavelength that is more or less based on UV wavelength around 405 nanometers. And therefore, you need to use a photo initiator that are active enough and also a quencher to help the resolution. In fact, if you don't add any quencher, you can have a certain concentration of radical that can push through the polarization, the photopolarization, and that can create some defect at the end. So therefore, you need a quencher to stop when you stop the light in order to get a well-defined object. And we use the polynipalm based on LCST, and we combine also a comonomer based on the pH-sensitive moieties, in this case, acrylic acid, that can combine two effects based on the temperature and on pH at the same time. Of course, when you try to implement that, you need to validate the approach. So you need, for instance, to use a photoreometer that, as you can have in the metallurgy, except that in the case of using temperature, you have to use a light, UV light, in order to illuminate the system, in order to induce the photopolarization. And you have to follow the viscosity against the rotation time. And you can see that when you apply a certain light, you have the first stage involving the initiation, so meaning the release or the decomposition of the radical that can attack afterwards the monomer with different pathway, but at the end you have propagation and crossling, and therefore you are building the system and you have an increase of the viscosity at the end. And this increase of viscosity is what you are looking regarding the 3D printing, particularly a window that we call stereolithography window that are between 2 and 4 seconds. You can use longer printing time, but sometimes you have some issue related to the definition of your final object. So you need to make a compromise using this type of processing window. Based on that, after validating the resin in terms of polarization, we show the design based on the modification on the surface area, the modification of the crossing density, and the modification of the chemical composition in order to get this actuation. The first examples that I will focus in the modification of the geometry. How to do that? Simply, you can see this flower without any anisotropy, very homogeneous. If you swirl in a good solvent, you can see that the system will swirl in an isotropic way, in a 3D dimension, because you don't have any geometrical anisotropy. But in this case, when you add some peaks, you can have, in fact, a certain anisotropy and then that will affect the swelling, and that will confer a certain motion when you swell in a very good solvent. To show that, what we have shown, we use this hydrogel S sub 10, and we play with the osmotic effect, meaning that we have to use a good solvent where we have the optimal swelling of the samples, and we use a bad solvent where we have the deswelling of your hydrogel, but should be also miscible. And we do a cycle, so we immerse in a good solvent, ethanol in this case, a bad solvent heptane, etc., etc. And by following the curvature, so the deformation based on the angles that you obtain here, we can show that our cycle is reversible. So you have the same position after doing this several times based on this osmotic effect. Of course, we wanted also to show that based on the photopolymerization, we can also play with the ghosting density simply by doing what? By playing with the photopolymerization time. So you can play with 2 seconds, 3 seconds, and 4 seconds. If you use a short polarization time, you have less cost system. When you use a longer polarization time, you have highly cost system. And therefore, playing with that, you can create a free layer by simply changing the polarization time. And this is shown here, the final product by following particularly the storage modulus against this photopolarization time, particularly the G prime related to the storage. We can see that when you use a short polarization time, you have a certain modulus that increase with the polarization time because you increase the costing density as shown here, 2 seconds, 3 seconds, and 4 seconds, where you obtain very highly cost network at the end. And of course, the G prime is also increasing thanks to this feature. And in this case, we play with the temperature. So we use a low temperature. In this case, the hydrogen swells very well. And we put afterwards the gel in hot water in such a way that we pass the LCST and we have the precipitation, the deswelling of the hydrogen. And you can see by doing that, it's reversible again and again by doing 4 or 5 cycles, showing the possibility to get this actuation. As a last example, in the case of actuator, is to play with the chemical composition. In this case, what we did was to play with the polymer related with the LCST, and we used the second monomer that I was mentioning, the acrylic monomer that are sensitive to pH. And we construct this actuator based on 3 layers, 100% based on polymer, an intermediate composition, and 100% of this acrylic acid comonomer. Of course, we evaluate the pH in the case of the pure polymer and the pure acrylic. And you can see that in the case of polymer, we don't observe any change because we don't have any moieties able to interact with the pH. But in the case of the acrylic, you can see that when you add a certain base, when you place on, in fact, in the alkaline condition, you can see that you have a swimming ratio that increases a lot because you have the deionization of the acrylic moieties. And based on that, we were able to show by playing with the pH, passing from acid to basic, this actuation showing up from this figure. Of course, and this is difficult because when you try to show that, but playing with the temperature and the pH, you can have a real bidirectional actuation, meaning that you can have this movement at the top, but also at the bottom. Of course, the problem is the gel is not well adapted for such when you swell, but you can show this bidirectionality. So in practice, it's quite difficult, you have to believe me, but playing with the pH against at the same temperature or using the temperature by changing the pH, you can have this bidirectional movement, but because of the gravity, it's not easy to have to see that based on this picture. So this is an intermediate examples where we have shown that we can prove this bidirectionality, we can play with the composition and so on. Another examples that I have enough time again for presenting, okay, is to develop ionic composite hydrogel that are mentioned here. So the idea is to have an ionic gel combining 2 features. A gel or the backbone, the polymer backbone, brings some ammonium along the system, where we incorporate silica particles having a certain complementarity in terms of ionicity. In this case, ion based on sulfonic moieties. And based on that, as I've already shown in some examples, you can have the ionic interaction that can modify the properties. Of course, when you try to implement that by 3D printing, you need to select the right photopolymerization condition. So you need to use the right photoinitiator that in this case also carry out in water for a lack of solubility for the system. And of course, we demonstrate the photopolymerization as already mentioned based on the relation with the storage modulus as you can obtain by this photoreology system against the illumination type. And we have shown by playing with the composition, so the acrylamide, this is the main component that is used for making such gel. When you add this ammonium, you can see a certain improvement and certain increase of the modulus. But of course, when you add nanofillers, as expected, you increase the stiffness in such way that you can see the storage modulus increasing a lot. Of course, the idea is to have a soft matters also that are deformable. And this is an example with the acrylamide containing 3% or in the absence, where you can see the stiffness improvement. But in the case of the combination with the ammonium comonomer with the silica particle, you can create a certain supramolecular network that are sustain a good deformation. Of course, what is very important is also to maintain a very nice dispersion. In fact, this type of interaction, you can see by 10 images that we have an individual dispersion of the nanoparticles at the end. The most interesting feature is the deformability. So instead of showing a lot of curves, you can see on the video the fact that with the finger, you can deform the samples, is the case Eiffel Tower, in a different direction, and you can maintain, in fact, the shape, and you can carry out that several times. This is what you can obtain from this curve strand. And also, based on the fact that you have some ions inside the system, you can have also a certain conductivity, as shown here. If you put an electrode and a diode, and you apply a certain current, you can see that you can light on the diode based on the conductivity of the samples. Of course, the actuation can be also maintained, because in this case, as already mentioned, if you play with a certain geometrical anisotropy, we can have actuation as already shown previously. One of examples is in collaboration with UBC and Sergi Pontoise, where we try to develop ionic tronic touch sensor. This is a concept that are mainly based on the difference of mobility between a mobile cation against an ionic system that are immobilized inside the gel. And when you apply a certain force, you generate, thanks to the mobility of the cation, a certain current, a certain difference of voltage. And this voltage can be related to a touch sensor. And depending on the force that you apply and also the position that you apply, you can have a certain voltage. And sometimes you can have a certain voltage can be negative. So therefore you can localize, in fact, the touch using this system. Of course, when you investigate this step, you need to control the mobility. So you have different regimes that are very important. But the second regime, what you obtain after a certain deformation, give a linear relationship. So therefore, you can have a certain monitoring of the touch, the force of your touch against the amplitude that you record at the end. And to show that, we took a gel that are containing a mobile cation and a mobile ion. And you can see that based on the difference of charge and using electrodes, we can see that in the case of the mobile cation, when you press, you have an amplitude that are positive. But when you play with an ion system, you have an amplitude that is negative. So depending on the way that you're building based on 3D printing, you can localize, in fact, the position based on the signature, based on the sign of your system. Of course, the composition is very important. If you use a low content of mobile cation or a very high concentration of mobile cation, you have also a difference in terms of amplitude. More you add, more your amplitude is increasing as shown here. In this case, you have 10%, you have an amplitude that is around 5 millivolt. And when you have a larger concentration of cation, you can see the amplitude increase a lot, passing 80 millivolt, for instance. Of course, the crosslink density is also affecting the mobility. So if you use a less cross system, so using 1% of crosslinker, that you have a certain very good mobility. When you crossing too much the system, you reduce the mobility, so therefore the signal amplitude is reduced, as shown here on these examples with the curve. Okay, based on that, we wanted to combine the 3D printing to create some compartment, getting inside this different feature. The ion type, so playing with from one compartment with mobile cation, with another containing the ion, or vice versa, playing with the charge density, but also playing with the crosslink density. And to show a very simple example, I will focus on the charge density. So this is an example. We make four systems: a system containing a low concentration of mobile cation, a system containing a high concentration of mobile cation, and we make two other samples. One containing a compartment that we associate with a low concentration of mobile cation against a high concentration, and we have the opposite situation. And when you press the system, particularly for these two examples, when you press, in this case of the system, where you start from a low concentration of mobile and you pass to a high concentration of mobile, you can see an acceleration of your signal, and you have the opposite information when you pass from when you press the compartment containing a high concentration of mobile cation against a low, and you can have a certain information in terms of mobility using this approach. Of course, based on that, we have created two compartments as shown here, where we have made a system containing more mobile and another system containing less mobile. And based on the position that you touch, you have a difference in terms of voltage. You can get a higher voltage or a difference of signal indicating the position of your final product at the end. This is my last examples, and I hope that I was not too long. Is to make structural rate matters in collaboration with Japan Nagoya University. In this case, we use systems that are able to interact based on the diffraction. The way that this works is very simple. We have to use a certain size of particle, in this case, silica nanoparticles, having a dimension that can interact with the visible wavelength. And based on that, you can have some diffraction of a certain portion of your visible wavelength, modifying the color of your system. This is shown here in a solution containing this gel before polymerization. You start from 0% to 41% of silica, and you can see based on the increase of the concentration of silica, you can see a change of the color. And what is very interesting is that when you take the gel and you do the polymerization, in this case, a free radical polymerization using temperature, you can see that the coloration that you obtain is maintained after polymerization. You maintain, in fact, the system after polymerization. And this is based, as already mentioned, based on the diffraction wavelength as shown here. And you can control, in fact, the coloration depending on the content. What we wanted to show is to use as a sensor. Because as particles having a certain distance, if you stretch or destretch the system, you can modify the distance, and therefore you can modify the visible light that you determine. And this is an example. We carry out a tensile test. 0% we deform at 50%, and you can see that you pass from green to blue to more dark blue using that. But it's reversible, so it means that you can stop stretching the sample and you recover the green color that you have initially from the system. And we try to implement that different color by using 3D printing in collaboration. So I hope that was not too long, but this is my conclusion, that I showed that additive manufacturing in terms of processing technology based on the chemistry, we can create very efficient, very adaptable matters at the end. And of course, you can have different applications based on stereolithography, could be self-robot and so on, but you have other type of application like biomedical application. I'd like to thank all the people that are involved in this research, and also Jeremy, because he's the leader for additive manufacturing. And I'd like to thank you for your attention. I hope that was not too difficult in terms of techniques, but I hope that you enjoyed. Thanks a lot.
Thank you very much. Thank you very much, Jean-Marie. I think, I don't know, I see Federica, Gabriella, Roberto, Gaetani. Do you want a question? We let you with exclusivity, just to become, if not, no? Gaetan, Roberto, no? Yeah?
I have one.
Go, Gaetan.
Okay. So thank you very much, Jean-Marie, for this very nice presentation. I have two questions for you. At the beginning of your presentation, you mentioned polymerization where you were using a photo initiator and a quencher. Is there an importance on the ratio between these two molecules in the polymerization? Do you have to control them, or you just have to put them in any ratios and it will work?
So it's a kinetic control. So it means that you have to play with the nature. So it's a kinetic control. So you have to play with the species that you add, your photo initiator and the quencher, and of course with the concentration. And you have to make, of course, if you use a very high concentration of quencher, that can stop the photopolymerization. So usually you add around maybe 1% of the total of the concentration. Oh no, sorry, 0.1% against 1% of photo initiator. So usually it's a ratio of 10 to have a certain photopolymerization ability, but at the same time having a good resolution. But because when you stop the photopolymerization, the quencher can act directly.
And is it something that is difficult to tweak actually to have the good ratio between these?
We use the photoreometer. So we adapt that based on the photoreometer.
Okay.
We play with the concentration, also the concentration of the monomer, because also that's affect the kinetics. And you can get this curve. And then based on the curve, you say, okay, I can use, for instance, 3 seconds for printing, maybe 4 seconds, 5 seconds, and so on.
Okay.
It's the way that we do. Of course, we can also do by batch using UV. So you apply 3 seconds for illumination time, but we don't like because sometimes you have the thickness that is evolving or so. Sometimes it's not reliable, and so we prefer photoreometer. It's true that batch is faster, but sometimes the information are not reliable. You have to be careful.
Okay, I understand. And in another example that you showed, actually you mentioned that playing on the polymerization time allowed you to get some polymers with different mechanical characteristics. What is the reason for that? Is it because the molecular weight of the polymer changes, or is it because there's some kinds of monomer remaining within the structure of the polymer or something like that, because the polymerization is not complete or something like that?
Yeah, you were right. In fact, we do a washing, but of course, when you apply 2, 3, and 4 seconds, the polymerization, the conversion increase. Usually at 4, even 5 seconds, we have more or less 90% of conversion. When you are 2%, you are more or less at 50, 60%. If you go below this conversion, the problem, the integrity, the physical integrity of gel is not present. So there are some issues. So you need to check all these issues when you do this approach in terms of printing.
Okay, thank you very much. Thank you, Diego.
Welcome.
Other question? Someone online or on site? Abdel, Rodrigo? Vale. Me, I have a couple of questions, Jean-Marie. Stereolithography. Can you do teeny specimen? I saw your plastic coatings, but can you basically what is the resolution, and can you go cylinder or mainly flat?
You can make any specimen that you want. The only thing, when you print from the head, you need a certain thickness. Not because you cannot go a certain dimension, but it's for physical integrity when you remove the gel. Okay. If it's too thin, you can have it can break. So, but the resolution more or less is between maybe a couple of microns and so on.
Okay, so very small.
But there's another technique that is called double photopolymerization, where you can generate smaller samples and are much easier in terms of integrity, but the definition is less, even less. So you don't have intermediate system where you can go to a system that can make a couple of centimeters, like I've shown today, against a samples that we have to make is a couple of millimeters. You don't have this intermediate. So there's the possibility to couple double photopolarization with stereolithography, but there's not a lot of examples available on the market.
And the stereolithography is expensive.
No, this one 500 euros. The only thing is that you need to use open source system, open system. When you go for strategies, of course, you can pay 50K and so on, but sometimes it's not good. Sometimes 2K, you can get a very flexible machine and you can screen a lot of systems.
And the raw material that you use, powders, liquid, monomers?
So it's usually liquid. So you can start from solid, but you have to make a solution from.
Okay, you need a liquid. You need to bring in liquid.
But there's another that is based on the sintering laser. But the problem, you need something that that can sustain heat treatment, high temperature. So usually you have to use polyamide, having a very high melting temperature. Because if you use PCL, that is a polyester, you won't get anything with sintering because you will have something that you completely melt at the end.
Sorry, I have a question related to what Diego mentioned that inspired my curiosity. When you say that you use open source software, how long would it take to someone who is not who is learning how to 3D print to learn the language or whatever it is to be able to operate this open source?
Open source means that it's not the software, it's the fact that you can modify the polymerization time. For instance, when you take strategies, you have there's some coverage having a chip. So you need to connect and then recognize that the polymerization will be that. Try to replace the resin and you assume that it's a material, it doesn't work at all and so on. So you need something that is flexible where you can modify the photopolymerization time, the thickness in terms of resolution and so on. When I say open source, to create the final object, you need to use STL object. So you need some graphical software, but now by 3D scanner, you can create directly your STL, but you need to 3D print. You can generate the file and then you introduce you download the file to your 3D printer and that can print directly.
Okay, so for the printer, you don't, like you have an interface where you choose the parameters?
You put a USB stick with your file.
With the file for the graphic, yes, but for these terms of temperature and all the parameters that you modify in the open source, you modify that on the code of the computer?
No, in the machine,
Okay,
in the software of the machine.
But thank you.
And my last question, Jean-Marie, is I really was very happy with your mechanical properties of the polymer that you show, the very noise resist, super elastic like this, and how long, do you have an idea? What makes so elastic and noise resist and you can play with for long?
It's based on ionic moieties. So it's not adhesion bonding. You form a certain ionicity around. You form like a nuage of charge.
Yeah.
So it means that this is not one-on-one. You break one bond and you have the dissociation. In this case, you have like cluster that can follow. In fact, for instance, you have this cluster that are highly concentrated of cation with anion. And when you detach, this anion is not solved. It's still connected with the cation. So therefore, they can have this deformation. And for instance, when you do a tensile testing with such matters, usually when you increase the speed, the system will break, shorter, faster, and so on. In this case, no, it's the opposite. Because you play with the ionicity, the dynamicity that is different, and therefore you recover more energy when you apply a speed that are very high. That's opposites that you can have with regular classical materials.
And these are, which other polymers have these ionic bonds?
Usually it's metacrilic, because this metacrilic, most of the monomer having such functionality can be metacrilic. But of course, you can implement in the case of polymer, because I didn't show, but for instance, we carry out a lot of reactive fusion on polypropylene to graph ionically, because we wanted to have a certain affinity with fibers and so on. But you can apply this ionic system also on the pre-existing polymer. Of course, it's reactive fusion, so maybe you won't get a very well-defined system, maybe some acceleration like costly, but it's possible by doing a post-modification if the monomer has some moieties on chlorine bond available, like a free hydrogen that you can remove by free radical polarization.
Super interesting. Thank you very much.
Thank you very much.
Last questions from someone? No? So thank you very much, Georgios. Do you have a question? I saw you connected. No, that's okay. Gabriel, Federica, I think we close, but in any case, Jean-Marie will not be so far. We can always reach by email. Thank you very much, Jean-Marie. And thank you very much online. Valentina, word of end.
Yes, thank you very much, everybody. And I will leave you for the next seminar. Have a good rest of your day. Goodbye.